I'm going to walk you through the USC DPS geofencing alert system. I'll cover the introduction, system architecture, and the high level design. So, in short, we turn phones into IoT devices, watch for zone exits, and send a personalized email alert. So, this is the DPS patrol zone, the safe area we care about. Our system treats this zone like a virtual boundary or a geofence. When a device moves from inside this boundary to outside, we trigger an alert. See, the problem is simple. People can leave the patrol zone without noticing, especially at high risk times. Manual monitoring doesn't scale across campus or run 24 by 7. So we automate it. Real time data plus personalized notifications to improve awareness. Here's the high level architecture. So there's device layer, the OwnTracks app on each phone that sends latitude and longitude. Then the IoT hub. The things board on AWS, EC2 ingests and manages devices. And then there's data store, the Postgres SQL keeps latest telemetry per device. And there's decision and notify, our geofence monitor the checks the boundary and emails the right person. So you can have a look at the image which explains the whole system architecture. Then there is how the data flows. So initially we ingest, the phone publishes location to things board over HTTP or MQTT, and we store the latest point per device in Postgres SQL. Then we monitor checks the latest point against the polygon boundary, and on an exit event we email the mapped recipient. So here's the image, which visually it's a pipeline like ingest, persist, evaluate, and then notify. The important bit is that we only act on meaningful state changes, not every single location update. Then there is the geofence logic. So our zone is modeled as a polygon of DPS boundary. Each new location is classified as inside or outside using a point in polygon check. So we alert only on the transition from inside to outside to avoid spam. We, we also track state, so re-entry resets things for the next valid exit. So here is you can see the path crossing the polygon edge, inside, then crossing, then outside, right? And then there is state machine which shows the rule like send only alert only from the inside to outside transition, right? Staying outside or moving outside to inside does not send an alert. So next we'll see the live demo and code explanation. Thank you.
Hello there, I'm Aditya and I'm here to explain the code logic behind USC DPS geofencing alert system. So the technology stack which was incorporated within the script was Python 3, PostgreSQL, ThingsBoard IoT, SMTP, Gmail's email service, the Shapely polygon creation, and JSON for user management. Well, first, we define a safe zone using the Shapely Python library. We procured nearly 17-point polygon boundary, which was present at the USC DPS petrol boundary zones. And these are the few examples of the different points given. The system architecture, how components work together, device location tracking, mobile devices send GPS coordinates to ThingsBoard IoT platform, data storage, ThingsBoard stores telemetry in Postgre, SQL, and then we had periodic monitoring with Python script queries database every 10 seconds. Geofence check Shapely determines if coordinates are inside or outside the petrol zone polygon. And alert generation. If the device exits the zone, a personalized email HTML email was sent via SMTP. So we maintain a JSON based user management. This helped to create a mapping from device to owner. The key features of this JSON file was mapped ThingsBoard device IDs to student email addresses, supports friendly device names for personalized alerts, easy to update without changing code, and auto-generates sample file if missing. Well, the database query logic, this was used for retrieving latest device locations. The challenge was getting synchronized coordinates. Latitude and longitude are stored as separate rows. We must retrieve both from the same timestamp. So you can clearly see that we are retrieving the latitude and longitude for a particular device ID for the same timestamp, and this result returns most recent location where both latitude and longitude exist at the same timestamp. The geofence detection algorithm. We first created the polygon object using the various latitude and longitude coordinates which we had from the USA petrol boundary zone, and we would test the point location to check whether the point is present within the polygon or outside the polygon. The algorithm that was used to detect the point location was raycasting. So the algorithm follows a procedure where it draws a ray from point to infinity and counts the polygon edge intersections. Now the odd indicates that the point is inside, and even indicates the point is outside. We use the smart state management. This helped us to prevent duplicate alerts. The state tracking logic went as follows. If the previous state was none, this indicated the first device check, and we would send the alert if the device was present outside the petrol zone. If the previous state was inside and the device was this indicated that the device was inside the petrol zone previously, and we would only send an alert when the device goes outside the petrol zone. And if the previous state is outside and the device remains to be outside the petrol zone, then no alert was given to the user. This was the code snippet which which governs this logic. The personalized email alerts, we sent out professional HTML notifications. The email body contained the device name and the status, the GPS coordinates, a timestamp, Google Maps link, and emergency contacts. Uh, this feature uses Gmail SMTP with app-specific passwords. So the continuous monitoring loop, which was the real-time operation of the script, it goes as follows. So we first connect to the database where the telemetry is being stored, query all the device locations, check each against the geofence, compare with previous state, send alerts for new exits, and update the device states and sleep for an interval. Now, the default interval was set to 10 seconds, but it is adjustable to 30 or 60 seconds based on needs. The console output example. So here are two output examples. One where the device is within the DPS zone, and the another is where the device is outside the DPS zone. All in all, the system summary key takeaways are real-time monitoring, accurate geofencing, personalized alerts, smart state management, easy configuration, and built-in diagnostics. So we enhance campus safety through technology and automation. Thank you.
Hello, I am Krish Modi and I will give you a live demo of the geofencing app that we've created for Lab 5. It will give you an email as soon as you go out of the DPS petrol zone. So we start by the Lab 5 IoT instance that we've created for on T3 large instance type and Ubuntu 24 LTS. This particular instance is deployed in the default VPC, and the security group has all inbound and outbound accesses to keep everything simple. Ideally, there should be permissions specific to a particular protocol, port range, or source so that we give the least privilege to the instance. But for the sake of simplicity, we are going with all traffic. Uh, Okay, let's go over the Thingsboard setup. So this is the dashboard, Thingsboard dashboard. We have created three devices. One is Krish's iPad, one is Krish's iPhone, and the third one is Aditya's phone. As you can see, all three are active. They are sending telemetry at every 3 seconds. This is Aditya's phone. This is the iPad. And this is Krish's phone. And we are utilizing all the data coming from these three devices for our geofencing app. We've also created a dashboard to see how the telemetry can be used. One of the ways, as you can see, is a time series chart of the battery power. Uh, it is similar to how the battery power is seen in your battery settings app. So I just attempted to make it like this. Um, Similarly, you see two maps. One is the map that shows you the current location. Right now, I am in my apartment. So as you can see, Chris's iPhone is currently in the apartment. Similarly, this shows you the routes I've been taking for various different things over last day. Um, I can actually increase the time window to see how many routes we've taken. So let's do 7 days. If we apply, you can see that I've been to the USC village. I've taken two different routes for the USC village for the testing of this particular lab, and you can see how I've been roaming around my apartment here. Then you can see my visits to Ralph, and because the DPS zone ends here, I've done a lot of testing for the geofencing app just by going out of it and seeing if I get the email notification from the app or not. So this is just an overview of how the IoT data is going over and how we are visualizing about the data. We can create the similar apps for the other three as well, but it's not necessarily needed because you can see how it's going on in here. Now let's go into the instance and see how the geofencing app is working. We'll first try to trigger the app manually using a curl command with dummy values outside of the DPS zone to show how it's working. And then we've also, on one of our trips, just to test out, we've recorded my phone on how quickly and how in real time we get the email. Like as soon as we step out, it sends you an email telling you exactly the security alert, and also shows you the latitude and longitude exactly inside the email, that can go out to the Google Maps to show you exactly where the person is. So it can be used as a safety sort of a feature as well. Okay, so let's try to run the GeoFence app. As you can see right now, it's inactive. I have opened two instances of the SH into the EC2, and right now it's the status shows that it's dead, and I've killed the um, killed the demon set 15 minutes ago. Now let's actually start by starting the service, and we're also going to monitor it consistently using the journal CTL command, which will keep showing us the constant run. So let's start here. Let's start this. You can see the three devices, and it has started the testing phase. And all the time zones are in UTC, and it will test every 10 seconds, as you can see, the interval. So far, all three devices are inside zone. We're going to test Krish's iPad and Krish's iPhone for this use case. I'm going to use a curl command to force a longitude latitude outside of the DPS zone. And you can see there are two emails opened up. The top one is where I'll get anything related to Krish's iPhone, and the bottom one will be the one where I'll receive anything on Krish's iPad. Now you can already see from one of our test cases earlier that I've gotten a geofence alert. You will shortly see the real time video recording when I receive this notification that we've shot outside for showing how real time it works. But let's jump back to our demo cases. So we'll start with trying to ping Krish's iPad as the one outside in the outside zone. I've taken the coordinate of the Beverly Hills, so let's try to do that. Okay, let the interval complete. Yes. So you can see Krish's iPad, it checks it's outside the zone uh, that we sort of like at this UTC time it received, and it sent the alert to my personal email. So if you see, this is how the geofence alert looks. You first you see the device name, its status, its exact latitude and longitude, followed by the time in UTC of where it receives. We've also added these two numbers to make it look like it's an automated message from the DPS monitoring system, you can say. And when you click on view location on the map, you can see it's the Beverly Hills City Hall. Another very interesting thing that we can notice from um, this is we can go to our things board dashboard and see if we can get the and yeah, so you can see that Krish's iPad was in Beverly Hills, though it was not in Beverly Hills, but we sort of forced it. So this is how you can verify that it's actually going through IoT Hub and coming into the platform. Now let's try something different. Let's so this is back in India. This is my home back in India, and let's try to ping this for Krish's iPhone now. So this is the latitude and longitude. Let me get the curl command ready for it. Here. Okay. Now let's try pinging. We expect to see this email come here, and K, and also we can also see that after the false after the check, Krish's iPad comes back to being inside zone because the on tracks from the iPad is pinging every few seconds already. So it places us inside the zone, and that's why in the next run it sees Krish's iPad inside the zone. Same thing we should expect from this. So let's run this, and you can see Krish's iPhone outside the zone. It's showing somewhere in India, and you can see here that we received another email. It's outside the patrol zone. This is the location. If we go into this, you can see it's back in New Delhi, back in India. Now for the sake of completion, you can see how it is. It picked up the longitude latitude that I placed for Delhi in the route map as well, because things would sees that I actually went to Delhi and came back within a second. Okay, so now we'll see how it works in real time, and I'm I've recorded this video next to Ralph, and the phone screen recording is overlaid on top of the video I took. So as you can see, I am refreshing for notifications. I'm still in the DPS zone. As soon as I start to cross the street, I will be outside of the border, and that's when I should receive the email. And this is the email, and you can see how it looks, and I can just click and it opens the Google Maps and it accurately shows that I'm on Vermont Avenue. Okay, now to summarize, we can go over some basic feature enhancements that we can do. First, we can actually do a time based monitoring, for example, um, checking every 30 minutes, or we can customize the time where it checks for the location, and we can have a snooze time based on the user. We can also add an SMS based alert, which is sometimes much more quicker compared to email, considering the Wi-Fi zone or not, if you have data or Wi-Fi or not. Uh, we can also set up multiple geofence zones based on users customization. So for example, instead of the DPS patrol zone, if a parent sort of wants to monitor their children, where they go for safety concerns, if they're traveling somewhere alone, or something like that, it can be modified for that. On a technical level, apart from features, we can improve this particular app by deploying it instead of being a daemon set, we can actually deploy it over a serverless repository, over a database, either through DynamoDB or storing all the values in S3, so that we can reduce the time to live on the EC2 to 1 day, and keeping the data for like 2 or 3 days retention on S3 bucket. So that way it will be slightly more professional and more production level. And we can connect it with a serverless repository deployed over CloudFormation stack, and through that we can basically build a production level app out of this idea. This was our demonstration for Lab 5, and thank you.